Okay, welcome back everyone to part 4 of today's lecture, where we now finally discuss the practical information or implementation on DFT or of DFT, so to speak, how to actually solve the Kohn-Sham equation. And we do that with a self-consistent field cycle or with the self-consistent field method to iteratively solve the Kohn-Sham equation, because as we remember, we need to compute first our effective single particle potential, which contains the density, and then we solve the Kohn-Sham equation. So the problem is that the potential depends on the density, which we want to calculate at the end. Okay, then let's start with the self-consistent field method. As I said, it's a numerical iterative approach to solve the Kohn-Sham equation. And the idea here is that we want to minimize the electronic density to find or obtain the true ground state density of a given system. Because from there we then can calculate the ground state energy and other electronic properties. However, in practice, we rarely solve the true ground state density, because it's a numerical approach. We iteratively work over and over it. So what we do in practice is we set a cutoff, a convergency threshold, where we are satisfied with the minimization. So we never really hit the true ground state density exactly, but we try to come as close as possible without using too much computational resources. How does the procedure look like? So we start with the initial guess for the density, then we update our effective potential, we solve the Kohn-Sham equation, we update the density, and then we start again. Okay, let's have a look on the scheme. I borrowed that picture from the SCF documentation, which is another DFT code, but it works also for any other DFT code and also for the GPO we use in this tutorial, or we use in the tutorials. Okay, we start actually with an initial guess of our density, right? We do that only once, so we guess the density of our system once. What we do then is we take the density and we place it into the effective potentials to compute the effective potential. With that, we actually solve the Kohn-Sham equation, and we then compute our new density from there, because we get out the eigenvalues and the eigenstates, and then we can compute our electronic density. And then what we do is actually we compare our current density with the previous density. And only if that is smaller than the setup threshold, where we are satisfied with our optimization, then we stop. But that's usually not the case for the first round, so we do the comparison, we see that the difference is larger than our threshold, and then we take the calculated density in this given run, and set it again up here, where we then calculate the effective potential, we solve the Kohn-Sham equation, we recalculate the density, we do now again the comparison with the previous run, if our density improved enough to fulfill our criterion, our threshold, our convergency criterion, and if so, and only if, then we see the self-consistent field cycle as converged. And from there we then can calculate our ground state energies, forces, eigenvalues, band gaps, all those electronic properties we are interested in. Usually I would say solving that cycle takes a couple of runs, depending on your system, how good your initial density guess is. For quite complex system, it can take quite a while, so we're speaking of a couple of hundred iterations to solve the cycle once. so it can be quite a time demanding process, but then at the end we will be rewarded basically with the true ground state, or close to the true ground state density of the given system. Okay, let's speak a bit about the single particle wave function, because as we see in the previous picture, right, we solve it and then we needed to recompute the density. And how do we describe it, the single particle wave function? There are basically possibilities to solve it numerically, but that can be quite computationally demanding for large systems, so it has been only done for a couple of small systems back in the 80s and 90s basically. So what we nowadays more do, and a quite very popular approach, is the linear combination of atomic orbitals, or LCAO in short. And that method basically had been implemented in the same way as the Rotan approach for Hartree-Fock. So that's basically where we get the idea for the LCAO method. The idea is that we can write a single particle wave function as a linear combination of basis function, of atomic orbital basis function. And because it's a linear combination, we scale it with the C value, and that provides us with a close approximation with the single particle wave function. And through the LCAO approach, our nonlinear optimization problem reduces to a linear problem. And that's really nice, because that we can actually solve with linear algebra. So solving it becomes quite straightforward and quite easy. By actually taking the LCAO approach, we end up with a similar expression, with the one here shown in red, as the Hartree-Fock method. Whereas the Fock matrix here, that the F operator, corresponds in that case then to a Kohn-Sham Fock matrix. If you're interested about this expression a bit more, let me know and we can discuss it a bit further in the tutorial. But in principle, that's how we solve, how we reduce our nonlinear optimization problem to a linear problem, and that has practical importance. Okay, how to describe basically those basis sets, or those single wave function within the LCAO approach, you might ask. So there are various basis sets available, right, within the LCAO method, and they all have in common that they try to approximate the single particle wave function. Two quite known approaches are one, the Slater type orbitals, as well as the Gaussian type orbitals, and shown here are basically the approaches to approximate a 1s electron, right? The Slater type is a bit more pointy, whereas the Gaussian is a bit more round, because the Gaussian depends on r square, whereas the Slater type only depends on r. And what we then do is we take a linear combinations, right? For higher orbitals, we sum up over a couple of Slater type orbitals or a couple of Gaussian type orbitals to actually simulate the wave function of a given atom. Okay, what are the pros? So first, those are localized basis function. They are quite efficient for molecules because we can describe orbitals quite efficiently. The cons is we get the basis set superposition error. So making by adding up the functions, we might up with basically an error by summing up, and that can become quite a problem, and then you have to correct for that one for larger systems. So it comes also with a drawback, that for sure. However, another approach, especially quite famous for solid states, because we have periodic boundaries, are plane waves or real space-based sets. And they are not to rely on the LCIO approach. So please keep that in mind. That needs to be closed up. So plane wave is just basically as exponent of r and a k vector. And what they are doing is, right, if we have here our pseudo wave function, and it basically oscillates a bit, and then it slows down and converges towards a given value, we can upset. The nice thing about the wave function is that we only have one cutoff value, the RC, where we cut off the plane waves and then we smooth them over it. So that's the red curve here, right? It basically underestimates the true wave function. However, because we take periodic boundary conditions into account here, mainly, it describes those long range consistent repeating interactions quite well. So for that reason, plane waves and real space-based sets are quite common for solid state methods. They also work with basis sets within the LCIO approach. I'm not saying that that's not working, but there are different codes, for example VASP, who uses a plane wave method. The pros is we don't have a BSSE error. That's nice. We can systematically improve it via an energy or lattice density cutoff, right? There's a single cutoff where we can basically increase the accuracy, whereas in the LCIO approach we need to add basis functions. And here we just have a single value, set the cutoff value, right? If we basically set it more like here, we get more inaccurate, or here we get also more inaccurate. So they're a good method to just approach it in that way. However, the contra is it's not very efficient for isolated molecules because they are expand quite long range into the void, and for that reason they are also not good for surface systems, for example, because in the surface system if we have a surface and then we put some vacuum on top, those wave functions expand also in the vacuum space, and we pay the price for that by computing those. And they are not great for strongly localized orbitals, right, or surfaces where the electron density is really located at the given place. Okay. Now we spoke about how to practically solve the Kohn-Sham equations for given position. But what we are doing quite often is we are interested in optimizing atomic structures, right? The SCF cycle, as discussed beforehand, only deals with the electronic contribution, with the density. But just imagine your task is to draw a water molecule, and you know, okay, let's draw a water molecule. It's the oxygen and then the hydrogen on either side, and you know that the angle between the two hydrogen and the oxygen in between is something around 119 degrees, right? So let's say you take 125, so you're a bit overshoot, but that's clearly not the true ground state configuration of a water molecule. So the idea is that we start with a given structure, and that's here the potential basically. And we optimize our water molecule, for instance, for example, by slowly decreasing the angle to finally end up with the 119.5 degree angle, and that's basically our minimum structure configuration. So how do we do that basically in practice? So we start with an initial structure, as said, with our water molecule, for example. We solve the SCF cycle with DFT, or then later in machine learning we solve it with a machine learning interatomic potential. So we get basically the true ground state density and the true ground energy, total energy for the given atomic structure, we use the energy then to compute the forces, for example with the Feynman theorem, we discuss it in a second. And then with the forces we can redisplace the atoms. So there are various optimizers available, quasi-Newton, like the BFGS or Gaussian process, process minimizers, and so on. So what they are doing is basically let's stick to our water molecule. They decrease the angle by a slight value, let's say from 125 to 124. Again, we recompute then with DFT and the SCF cycle our energy, get the forces, and do that over and over and over again. And by doing so, we basically lower our energy from time to time, from iteration to iteration, until we reach hopefully the global minima. We have to point out that depending on your energetic landscape, it might be also the case that you end up in a local instead of the global minima. And in principle, it's hard to estimate if you're actually in the true global minima or if you're just in the local minima. So also setting your optimizer parameters in a decent way is quite important, because what it does, it always moves forward your atom configuration in a given step width. So for that, making the step width not too small, because then you end up infinitely while optimizing, but setting it too large, so how much you displace the atoms at each iteration, then you might overshoot the local minima. Right, you then, for example, if we stay in that picture, you go from here directly to whatever here. So you don't, you miss the global minima. And again, we set up a convergency threshold where we say, okay, that the change between the previous structure and the current structure is low enough, and then we set up that the structure are actually relaxed and converged, and that's basically our final structure. So in that case, it would be our water molecule with the 190.5 degree angle between the water and the oxygen. Okay, and how do we calculate the forces? Because those we need to move the atoms within each iteration, or also to adjust lattice parameters. So basically the forces are obtained by the negative derivative of the energy. I think that's clear to everyone. But how do we do that in practice? And there the Hillman-Feynman theorem comes in, because the force depends only on the particle density, which is quite nice, and also on the nucleus potential and potential. So for that we can basically, right, that's our external field potential, that's our nuclei potential, and that's our density, and by solving it we get the forces, and we can use the forces, we quickly jump back, we can use the forces here to optimize our structure by displacing the atoms a bit, and then use that structure again as the input, calculate our energy, the forces again, and we do that in the loop again, similar to the SCF cycle. And we solve the SCF cycle in DFT to obtain the energy, or then with machine learning interatomic potentials we use it to obtain machine learning interatomic potentials. Exactly. Okay, at the end maybe some practical informations, and that slide was an idea of my colleague Andre Krejci, so I want to give him the credits here. What should you do if my SCF cycle, or also your structural optimization, does not converge? Mainly focusing here in GPO, because that's what we use in the tutorials. So first of all, I mean, it sounds a bit trivial, but first of all, check the documentation. It's always a good start with checking, did I miss something? Have I misplaced or misset some parameters? Stuff like that. Second one is check your convergency criterion, right? The thresholds. For energies, that's basically for the SCF cycle, or the forces then for the structural optimization. They might be too tight, right? They might be, you might, whatever, set them way too tight, and then you never really converge because it can't reach that threshold. Check your K points. We will discuss it in the next part, in the last part of this today's lecture. It's basically an integration grid to obtain the density, and if you set that one too tight, it also affects your SCF cycle. Check your initial guesses, whatever, for the basis set, right? Are my basis set, for example, too tight? The atomic moments, charges, all that influences the SCF cycle, and also your structural optimization. Also check your smearing parameters. Usually you have at the Fermi edge, if that's our Fermi edge, and that's the energy. It's a step function because we do DFT at 0 Kelvin. That's really important to take into account, right? That's the side where everything is filled with electrons and that's empty. So that's the Fermi energy. Fermi. And at a given temperature, that's not a step function. It's more like a smearing value. So you can also check the smearing value, but that's quite advanced, so don't do that in the first place. Check the density mixing parameters, like the Poulet mixing parameter. Check the eigensolvers, that's then more like GPO related. Check the Poisson solver, also GPO related. And if you have spins in your system, check the spins. Did I misinterpret the spins, for example? So there are a lot of stuff to check. But start systematically. That's really important. Don't change 10 parameters at once and then rerun it and then still realize that it's not converging. Change one parameter at the time to basically narrow down the error or the problem. By doing that, you basically know, okay, I changed now the eigensolvers, for example, and it now converges. So the problem was more likely the eigensolvers instead of changing the threshold, right? So do it systematically. That's my advice here. Okay, with that we're at the end of the part of the practical implementation part of DFT, how to solve the Kohn-Sham equation. So we discussed how to solve them with a self-consistent field method. We discussed also the necessity of basis function, different methods, the LCAO or the plane waves real space basis functions, how to optimize atomic structures, how to solve forces, and finally what should I do when my SCF cycle is not converging. And then in the last lecture we will actually discuss some practical informations for molecules and solids. So that actually gives you some understanding what actually DFT can be used for and what we can't compute. Okay, thanks.